Okay, number one, let's make a diagram first. Okay, you have two small spheres having a mass of 0.075 grams suspended by a silk thread from the same point, okay? So what that means is you're actually going to take two silk threads and you're going to suspend it from the same point. So same point, and then so you're going to make it float, right? And what happens is when given equal charges, they separate, they split up, okay? And why would they split up? Because the charges must be the same. They will repel. Do you guys remember the mini that we did on electrophorus? Those jars, Leyden jars, okay? So what happens when you charge that little knob, metal knob, remember they split up? The foil plates split up. So this one is making an angle of 23 degrees with each other. So let's draw the vector diagram. So here's the silk thread. So making it more realistic there. So this is the angle of separation. It's 23 degrees. So here are the spheres. So you got these two balls separated at 23 degrees with each other. What is the electrostatic force acting on each sphere? So we're looking for the electrostatic force. Okay, so we have the mass in grams. You have to be 0.75, so you're going to divide it by 1,000, right? So this is 75. So that's going to be, I'm just going to go, well,
7.5 to the power of -5?
Yeah. And when you divide it by 1,000, you have to make it into kilograms, right? And then it says here 35 centimeters silk, so that's the length. What do we do with that one? So this is divided by 100, right? So this is 0.35 meters. So that's the length of the silk thread. Okay. So those are the masses of each one. What else do we know? We know the mass. We know the length. All right. Okay, so what's happening here? So first they're lying straight down, right, because of the FG. And then they split up. So they went up that way, 23 degrees. So how do we calculate the electric force on each of these? Why is it suspended? What made it suspend? What made it split up?
It's kind of like that little tin we put the
Yeah, exactly. So two forces here are balanced, right? So you got your Fe equals Fg. It's kind of like the Millikan experiment, except it's not on a parallel plate. So these are charged and they are like charges, so they repel. Okay, so what do we know here? You're looking for the electric force, one here, and the Fg. So what do we put for the Fg? Well, Fg is either mg or it's also g m2 over r squared, right? So that is another formula that we can use for the Fg. Since we're looking for the electrical force, that has to balance the gravitational force to make it suspend. Okay, so that's basically what lifted the spheres. So we can go g m1 m2 over r squared. But here's the thing, there are angles, right? Because if I were to now just draw the Fg, Fg should just be going straight down, right? That Fg should be going straight down. Okay, so that's the original position right there. And then you applied the electric forces, so that made it go up. Now it would have suspended it, except no, you still have the Fg, so you're still being pulled by gravity, and the electrical force is what lifted it. Okay, so these two are equal. Okay, so if this is the Fg going down, we're gonna have to find this one right here is the FG. So we need to incorporate that angle of 23 degrees. So we need to redraw this. Okay, so why don't you guys do the calculation here first for the FE. Okay, I'm not gonna have room to write everything down, but go ahead and calculate that for me, please. So G is 6.67 times 10 to the negative 11. Okay, what'd you guys get? Okay, let's think about it for a second here. Here's the triangle now, right? That's the 0.35. That's the length of the silk thread. Okay, this is the FG. The FG is the line going right down, right? So we need to find this line right here in terms of forces. So what would that angle be on the side? Half of 23, right? Which is? What's half of 23? 11.5, right? So that's 11.5 degrees. Okay, so this line below is the FG. FG right here. Okay, we need to get this. What do we need to use for the R right here? The distance between the two charged particles, right? So we're actually looking for this line down below. So this is that's 90-degree triangle. So we need to find this angle here because this is the separation between the two particles, right? So we actually need to find this side first. So we can't just plug it in into here, right? Because we're looking for the separation between the two objects. You guys remember when we covered the gravitational fields unit? That R is the distance between the two. Okay? Now, yes, the R has to be taken from core to core, but this is a very small object anyway. So we're just gonna have to find this distance here, and that will be, what do we do then? Once you find this distance, okay, can we do that first? What do we do to find this? Use SOHCAHTOA, right? Opposite over hypotenuse, so sine. So let's do that first. So sine of 11.5 degrees is x over 0.35. Okay, let's find that x. And then double it, yeah. What'd you get? What did you get just for this one here? 0.06, right? So this is 0.0697. So then you're gonna double that to get the other half. Okay, so times 2. That will give you the entire x down at the bottom. Okay, so this is the R, 0.1396 meters. Okay, so that would be the R that we're gonna have to use, because that's the separation between the two charged particles, right? Okay, so now that you calculated the R, that will give you the Fe. I'll actually write it down here. Let me just square that because it's the same thing. So the R is 0.1396 squared. That's going to give you the Fg, which is equal to the Fe. Okay, and I got, can you guys double check? 1.93 times 10 to the negative 17. You got the same one? Okay, I did it twice and I got the same answer. How are you guys doing? Okay. The only thing that was tricky with this one is the angle was given, so we can't just use the length of the thread. Okay. When you're looking at the R has to be the distance between the two objects. Okay, let's, you know what, because we're taking this question out, I'm going to extend that question, okay? So part of this question now, let's call that question B. Calculate the charge on each sphere. So we're looking for now the Q. These are identical, right? Q1 is going to be equal to Q2. Can we find the charge now? Okay, I'm going to give you guys a little bit of time to do that. Okay. Okay, so because the charges are equal, you just isolate the Q. So it's Q1 times Q2, which are identical. Q times Q will be Q squared, right? So then once you isolate that, you got electrical force R squared divided by K square root. Okay, so plug it all in, take the square root, and I got 6.46 times 10 to the negative 15 coulombs. Now if I ask you, question C now, how many electrons would have been gained or lost? Now, on the question here, is there a way that you could actually tell if this is a positive or negative charge? You can't, right? It doesn't say. It doesn't tell you. So the last question I would ask here is, how many electrons would have been gained or lost? Because we don't know what charges they are. Doesn't tell you. So what you do now? What's the last step? So you have this charge, got this many coulombs of charge. To figure out how many electrons you would have gained or lost, what do? The last step. You divide it by the, yeah, that's right, charge of electron, which I'll give you also in the constant, 1.6 exponent negative 19. So that's a lot of electrons, and usually that's what happens. So 4.04 times 10 to the power of 4 electrons gained or lost, because we don't know the charge, because that was not a question, we just added those. Okay.